So let's now think about how we calculate sums and the product of sums, because we're going to need this kind of thing when we start looking at value functions in reinforcement learning. So it's easy to calculate the sum over single elements. So we can represent the sum across element A1, A2, A3 all the way up to AN in the sequence by the sum sign. So it's just written down in terms of the index on the element, and we just sum it up between the limits that we want to sum it up across, in this case 1 to n. And if you consider a trivial example, we have 3 values that we're going to add up. Let's say A1 equals 10, A2 equals 20, A3 equals 30. To sum that up, it's trivial. It's just going to be the first plus the second plus the third elements, 10 plus 20 plus 30, it's going to be 60. What we can also do is compute the product of 2 independent sums. And when I say independent, it's because AI only depends on I and BJ only depends on J. So we can calculate the sum across all A's and then multiply it with the sum across all B's. And we can think of that as, first doing B and then multiplying, calculating that sum and then multiplying that with the sum across all A's. But we can also multiply them out and consider it as being the sum across all the B elements multiplied by the sum across all A elements, and then have indices basically that just go across both the A and B, which is quite clearly written here, which is quite often written just with a single sum sign. This is just saying we're going across all A and all B elements and multiplying all of them together and adding them all up. And sometimes it's just written as a sum in this fashion, just indicating that we've got element A and element B, and we multiply together all combinations of A and B together and add them all together. So let's think about what that actually looks like when we multiply it out in terms of sequences. So the sum across all A multiplied by the sum across all B, we can think of as expanding that out like this. So we have all the A terms that we're adding together, and then we're multiplying them with all the B terms adding together. And clearly what we can do is we can represent this as, first of all, we can put a sum back in there if we want to. We can say, look, this is just the sum across all A elements, and each A element is multiplied by the sum across all B elements. And that basically looks like this if we multiply it out. So it's A1 times the sum across all B elements plus A2 multiplied by the sum across B elements, and so on. And that's what all the terms will look like if we actually then multiply out these terms here. So it's A1 B1 plus A1 B2 plus A1 B3 blah blah blah, all the way down to AN B1, AN B2, all the way up to AN BM. And then we have to add all of these elements up together. And that's how we get this formula, and that we can actually split it up into, rather than doing the sum across all A multiplied by the sum across all B, we can just sum across all elements of the product of the elements. Okay. And let's now consider a trivial example. We've got 3, actually that should say 2. We've got 3 A values. Let's say A1 is 10, A2 is 20, and A3 is 30. I've got B1 and B2, 100 and 200 respectively. This obviously leads to the following sums. We add up across all A, and we got 10 plus 20 plus 30, which gives 60. Add up across all B. In this case, it's just 100 plus 200, which is 300. If we use the first formula, we multiply the sum across A with the sum across B. It's then 60 times 300, which is 18,000. We can also do it, again, it should be 2 values of B, in a slightly different way by multiplying out the terms of the products. So let's find out, what are all the product terms, where it's going to be A1 plus A1 times B1, right, which is 10 times 100, plus A2 times B1, which is 20 times 100, which is 2,000, A3 times B1, 30 times 100, which is 3,000, and then we go through the same again, but with the B2, so A1 B2, A2 B2, A3 B2, and all we do then is just sum up all of those, in this case 6 values, and of course we get exactly the same result. It's just we've done it in a slightly different way. Now, one of the reasons this is something we need to think a little bit about is because we're going to be using sums and weighted sums to compute expectations of value functions when we're looking at reinforcement learning. So let's think about, first of all, what kind of probabilities and stuff we have, because we want to think about expectations. So when we're doing reinforcement learning, quite often we're in a state S, and we want to know what the policy is. So the policy is basically what action do you take when you're in state S. And this is often written as pi, A given S, and this gives you the probability of the actions given the fact that we're in a given state. And quite often A will be stochastic, so there'll be a set of probabilities for different actions, and we're thinking about the case where there's going to be a set of discrete actions. So imagine we had a state S. We're in a state S. We're not talking about any other states, but this particular state is going to be associated with 3 actions, and the probability of taking them we can then define in this particular example. We're going to say, given we're in state S, the probability of action A1 is going to be 0.1. Given we're in state S, the probability of action A2 is going to be 0.2. And given we're in state S, the probability of action A3 is 0.7. Now, because these are probabilities, and in this case there's 3 discrete actions, then clearly across all of the actions it's got to add up to a probability of 1, because we've got to take some action, and the probability of taking some action is definitely going to have to be 1. Now, in a general scenario, when we're in a state and we take an action, what's going to happen is we'll move to another state, right? So that's what the transition probability describes. It basically says the probability that we end up in state S prime, given the current state and the action, is going to be a probability across all possible future states. Okay, so this is the stochastic transition probability representation. We're in a given state, we take an action, and we end up somewhere else with a certain probability. If this was a deterministic function, it wouldn't be a problem. Well, we'd go to another state with probability 1, but we can still capture that condition using this representation. So let's now consider the case when we've got 2 future states, S1 and S2, that depend on the 3 actions that we've got up here, A1, A2, A3. Let's just say, as an example, we're in state S, right? And we take action A1. It's going to define here that we go to state S1 with probability 0.5, and same thing is that we go to state 2 with a probability 0.5. Let's now think about what happens if we take action 2, and let's just say as an example, we take action 2 and we're going to go to state 1 with probability 1 and state 2 with probability 0. So although the first row here is actually a stochastic transition, we see that the second row actually is deterministic. So we end up, if we take action 2 and we're from state S, then we definitely go to state 1. And we can also define as an example what happens when we take action 3. And if we take action 3, we're going to say, well, we never go to state S1, but we always go to state S2. Now, in reinforcement learning, what's going to happen is we're going to be in a state, we're going to take an action, we're going to move to another state, and this moving from one state to another state is going to be associated with a reward value, which could be positive or negative. So we want to be able to define what's the reward, the future reward of moving from one state to another state. And we're going to define it in this particular case just for these 2 future states. So what we're going to write this down as is g of t s to s prime. So when we're in state S and we go to state S prime, that's associated with a reward. Now we're writing this down in terms of being in a state and going to another future state because we don't necessarily know on the basis of action where we're going to end up. But if the state transition is actually deterministic, so the action completely specifies where we're going to end up, then we could actually write this function down in terms of the action rather than in the future state. But that's just so you've seen that form of it as well, right? But state current state to future state is always right. Given the state and given the action is right as long as it's deterministic. The state we end up is deterministically dependent on the action we take. So let's imagine now we take, we're in state S and we end up in state S1. Let's just say in this case we get a reward, a future reward of 10. And if we end up from state S in S2, we get a future reward of 0. That's just as an example. Now what we care about in value function estimation is we're going to, and we'll see this in a bit more detail, we want to know the value, the future value of a state S, and that's going to be the expected value of this future reward. And how do we calculate expected value? Well, if you remember, to compute expected value, we've got to look at all the values that we can get, and there could be a discrete set of values, and we look at the probability that each one happens, and we calculate the value multiplied by its probability, and we sum up across all possible states that we could end up in, right? So it's just basically a weighted sum. And in this particular case, our probability of ending up somewhere else is given by the joint probability of the policy. So there's a probability that we'll end up in a certain action, and then there's a probability that we'll end up in a future state given the action that we took as well. And of course, both of these depend on what state they're in, but that's not something we need to actually sum across. And then the reward is going to be given by the state we're in and where we end up. So, in other words, state value is going to be given by, let's think about these two front terms. These two front terms are the probability of a particular reward, and the second term is the reward. So we have to sum across all actions and all future states, because those are the things which can basically, where we can end up, the probability we end up getting this particular reward, and this will then give us the value. We'll come back to this in a lot more detail in the next sections. This is just to sort of see how it fits in with our sums and weighted sum business. So let's think about this value then. How do we calculate that? So let's just put some hard examples in to make it very clear. Given that we've got this policy in state S, we have action 1 with probability 0.1, action 2 0.2, action 3 0.7, and given then now our probability transition matrix, that if we end up in state from state S, take action A1, we end up in state S1 with 0.5 probability, and in state 2 with 0.5 probability. Take action A2, we end up in state 1 with probability 1 and state 2 with 0. And if we're in state S and we take action A3, then we end up in state 1 probability 0 and state S2 is probability 1. What we need to do then is also take into account what the reward is in this case, because we care about this reward term. So we've just said that if we're in state S and we go to state S1, we end up with a reward of 10. If we go to state 2, it's 0. So we've got to calculate now basically all of these terms and add them up across all actions and all states, all future states. So this is going to be then all just like we did before. It's going to be the sum of the product of all of these elements. So it's going to be what happens when we're in. Let's do first of all start off with A1. When we take action A1, and the probability that we end up in state S1 multiplied by the gain we get from going to S1, plus probability again we take action A1, but we end up in state S2. So this is doing this sum here, multiplied by the gain we get in S2. Then we do the same, we add on again, because we're summing across all actions and all future states. We do the same thing for A2. This case is, now we're saying we're summing across all the values for A2, of A, which is now A2. And again, the probability that we're in state, we go to state S1 given A2, and the gain that we get from being in S1, and exactly the same thing here for being in state S2. And then of course the third thing is that then what happens is we add on what happens if we take action S3 in exactly the same way. We put in the value functions here. We can work out the value functions by adding up all of these terms. So all we're doing here now is we're just substituting in all of these terms. So the policy of getting A1 given S is given by 0.1, so that's where this 0.1 comes from. Here's the transition probability that we take an action A1 and end up in S1, that's here, 0.5. And the reward that we get if we go from state S to S1, we just substitute that value in, and here we get 10. And we just do that for all the combinations of these things that we've written out here, and we put in the numerical values. And what we'd see in this particular case is we'd end up with a value for the state S under this policy, right, this is the policy of 2.5. And that basically is value evaluation of a state using these sums.